So we did two different collections early on the other day. One was a simple array list, the other one was a simple linked list. And so that was quite fun with using ChatGPT. Now what I want to do is to make a very simple binary tree, not a balanced one, AVL tree, or a red-black tree, but just a very simple one. Of course, the problem with the simple one is that if it's not well balanced, we can have very high lookup costs. I also want to add a contains method into the simple list that we wrote, the previous one. And if you want to look at my previous ones, have a look at LinkedIn. My LinkedIn profile has the old ones. Twitch has the latest ones. It might go off, and I'm also putting them on YouTube as well. So if you search for me, you'll find them there. All right, so let's give this a try. So what we're going to do is the following. We're going to go to this little broadcast over here. We're going to add a class simple unbalanced binary tree. This is just I say unbalanced because it really should be balanced, but we're not going to do that now. And it's going to be off the T, and we're going to say, well, let's just generate some code. So let's make generate code, and this, of course, again, the integrated AI insert IntelliJ. You can do the same thing directly on ChatGPT if you want. And here we're going to say, please generate a simple unbalanced binary tree. Okay, let's see what it does. So it's going to hopefully generate something useful. It's got a root node. The node is going to have left and right, I'm going to assume. It's got an add method. The add has the current, the add will do that. Okay, so that's fine. And then it just basically goes left and right and sees whether or not it should add it. Now, this one actually uses the hash code. I don't really want to use the hash code. What is the hash code? I guess they're not using comparisons. And if it's equal, yeah, this is not nice. This is a bit too simple. Let's specify a bit more. Use comparable to order elements, because so basically what we're saying is we want to use comparable, not to just use hash codes. Hash codes, okay, now that's not right. At T extends comparable, that's right, sorry, it is right. I thought they're making the tree comparable. So then we're not taking the hash code anymore. We're going to say and basically what we're saying is if the comparator is equal, we're considering them as equals, So which I think is okay. We'll leave it like that. We'll keep it simple like that. Actually, I don't know what happens with the normal tree if you have two which are the same. But this is super simple. And let's specify some more. Add a contains method, so we can see whether a value is contained in there. Probably also want to add a remove method. If we add a remove method, we're going to have a pointer to the parent in order to be able to remove it. So maybe we'll leave out the remove. The contains basically goes through and sees whether it's there, and that's a binary search, which should be fairly fast if it's well balanced too, but this is not a well balanced tree. So let's do one more thing, which is add a remove method, and I predict it's probably going to add a pointer to the parent, because if you don't have a pointer to the parent, it's going to be kind of difficult to remove elements from there unless you keep the previous one. I guess you could keep the previous one as well. It becomes more tricky. So we'll see if they've got remove. Remove now. So the remove method, which, okay, we'll see if it works. Okay, so this is now a binary tree. The constructor's there. It doesn't actually take it doesn't do anything, so we'll delete that. I'm going to repurpose this, the simple list test, to be for simple tree test. And we'll obviously change this to be simple tree test will be a normal class, and I'm going to have a simple unbalanced binary tree inside here, and we'll call this a simple tree. So we're going to create over here, should return that one. And for now, we'll make it non-abstract. We'll just say protected create equals return new simple unbalanced binary tree. All right. So that's good. Oh, we need a size. We haven't got that yet. So let's add that in here. Let's go back to our simple tree. The size is fairly easy. And we also should have an iterator as well. So let's add that. Generate code. Add size and implement iteratable. Iteratable. I can't spell that. Iteratable. How do you spell iteratable? I'll just make the same mistake as last time. Iteratable. Iterable, not iteratable. Iterable, of course. Okay, so implement size and iterable. And iterable. There we go. So that should now hopefully add these two methods. The should be. I don't mind if the remove doesn't. The remove should work. Okay, so the size they keep. Oh, they just keep the size. I guess that's reasonable. They can just remove the size. And it's still generating the iterable stuff. So the iterating, they're going to iterate. They've got. Oh, this is interesting. They basically build up a stack. Why do they just use deck, array deck? That's kind of weird. Let's specify use array deck instead of stack. Array deck is a much newer version of something like a stack, double-ended queue. And it's definitely what I would use. I wouldn't use a stack. Stack is an extended vector. Now, there's nothing wrong with it as such. I mean, I do use vector sometimes. Vector's not deprecated, but might as well use array deck. Well, at least we have a time for coffee. That was all this is going. This is a really nice cup from Devox, Belgium. Of course, they'll have great coffee in Belgium. So now we're using array deck instead of the stack, which I think is a better option. So let's see how well this works. Going back to our test, our simple tree test, getting at an index we don't need to support, right? So that's definitely not something we need, but what we do need to see is whether it contains it. So it assert true. Simple tree dot contains the test string, so it must be able to contain the test string, right? So we need that one. Where else do we have errors? Okay, it's again the get 100. Again, we're just going to say assert true simple tree dot contains test 99. Why does not work? Oh, simple. It helps if I type the right code here. Index out of bounds, or no, that's not going to work because you're not going to go out of bounds. Again, contains. Don't know if that's going to be useful to have this test. True. Okay, that looks okay. Remove at shouldn't work. We don't have remove at, so let's delete that one. Or we can just say remove, test remove. And I wonder what happens if we call remove on something which isn't there. It shouldn't give an exception. Not there. I wonder what remove actually does if it's not there. If it contains it. If it contains it, removes it. So it basically will remove it if it's there. If it's not there, then what? It just does nothing? I think it does nothing. So I'm not going to be too unhappy about that. I'm just going to test for that. And probably what you want to do is to return whether or not it actually removed it. And we're going to just remove this again. Remove just the string. And yeah, I'm not sure about this one. I think I'll leave this one out because if I remove items from the tree, I mean, I could do this. I could say while true, well, let's I can say not remove at because we didn't have remove at. Don't know why it's offering us that. Maybe because it's referenced later on in the files. I can say or while iterator string it. Okay, do okay, so here's what we'll do. We'll do it like this. While it equals it dot equals simple tree dot iterator dot has next. Okay, so we're doing assignment at the same time. While has next simple tree dot remove it dot next. So I'm not removing with the iterator. I could do that, but I'm just making lots and lots of iterators and removing with it, and at the end checking that it's empty. All right, and the rest seems to okay. The FIFO queue. The FIFO queue actually will of course not work, but what we do want to do, which will be interesting, is to add a bunch of elements and see what the time is. Let's add 1,000,000 elements to that. We're going to add 1,000,000 elements, string plus I. And then what we're going to do is we're going to see whether or not it contains it. So we're going to do for 2000 assert false that simple tree contains not there. So there's no string not there, but it's got to look through the whole thing in order to see that it's not there. And because this is an unbalanced binary tree, it's going to be like very, very slow. Well, fairly slow to do that. It's got to go through the whole tree every time. And it's not balanced, so it's going to be pretty bad. So let's run the test and see whether the test passes, whether the binary tree is even correct before we get too excited. Okay. So the fast fail iteration, that doesn't work. All right. I'm not that unhappy about that, but we can add that quickly. That shouldn't be too hard. We'll go back to the simple unbalanced binary tree. And what's it complaining about? Cannot access. I cannot access it. That's weird. Of course it can access it. That's strange. Private static. It's like complaining about something which shouldn't be a problem. I don't know if this is an IntelliJ problem. It's weird. Don't know why it would do that. Anyway, okay. So let's generate some code here. Actions, and we're going to say generate code. Make iterator fast fail. We did that last time, or the first time with the list. And hopefully it'll be able to do that. Just add a mod count. Every time you change it, you increment the mod count. If you add, if you remove, you increment the mod count. And then you have that mod count also inside the iterator. So this is pretty much the standard way of doing it. Expected mod count. And if it changes, then you cause a problem. You throw an exception. So I think this should work. Accept all, and let's run the test again. And now there are some issues here. Contains. What's happened to contains? Maybe I was too hasty. What happened to my contains? It like yanked away my contains. Why would it take away my contains? I love my contains. This again going wrong. Contains. There's my contains. Contains had nothing to do with the mod count. So if you're too worried about this taking your job, don't worry too much. Don't worry too much. You're going to be in a job for a while at least. Let's try it again. Make the iteration fast fail, not deleting the contains method. Contains method, please. I added the please just to be polite, and hopefully they won't yank it away this time. Okay, so mod counts there, add is there, updating add, should update the remove. Now, of course, we could do all this by hand. I mean, it's like, and sometimes I wonder if it's just not quicker to do it by hand than to do this with AI. If you're a really bad programmer, maybe AI will make you faster. Pretty sure it'd be done by now, like a long time ago, if I did this by myself. What's interesting about AI is, I find interesting, is how what they do is they basically do the let's see what they're doing here. Okay, let's see if that works. Do we still have the contains? Contains are still there. Okay, good. We've got contains. What is interesting is if you ask it to generate documentation, let's just do that. Let's say generate a Java doc, generate write documentation. What it often does is it will go and show you the implementation details in the Java doc, which is not what you want. Most of the time you want to have, I mean, this one's not too bad. Normally you want to have the interface, not the implementation. This one's kind of obvious. Alright, but it doesn't say information about whether it's fast, fail, iteration, and so on. Let's run the test again and see if it. Oh, it's taken away my size. It like gives me something and takes stuff away. Come on, seriously, don't be like that. Oh, man. That's why we've got unit tests, right? Okay, right. Generate code, add a size method. Kind of mean, because it's like, you know, what might be worthwhile is to start off by saying, I want all of these things: fast, fail, iteration, size, contains, remove, and then it actually might be able to do it. But sort of adding new functions like this sort of seems to be more problematic. And I don't know why they take stuff away. And I don't know if this is just the AI that IntelliJ is built in. I don't know, no idea. But it's certainly interesting. It's 85, 80%, 91% generated, 94%. Okay, so let's accept all and see whether that works. Yeah. Doesn't work, but at least. Okay, the iterate remove is not implemented. And test remove, add remove. Oh, this is interesting. The remove doesn't work. The size doesn't work inside the remove, because if it doesn't actually remove it, it still sets the size to -1. So the remove should only work if you actually remove something, right? So your remove should return true or false, whether or not removed it. So basically, the size minus minus and the mod count plus plus, that should only be done inside here when we do the actual removing, right? So the actual removing is done, I guess, over here. I think that's where it's doing. Node with 2 children, find the min for the right, replace current value by that minimum, and delete that minimum. Yeah, I think that's probably what you need. So only when you do the actual remove will you want to do that. Now that also is wrong. Test remove is still expected 1, and maybe it doesn't do it correctly now either. Add test string, remove test string. So the actual is 1. So now I might have put it in the wrong place. The mod count and the remove. Interesting. So let me go back to the remove. You can see this is live. I mean, if anything, this is live. So basically, I guess what could happen is that if there's only one element, which is the case now, if current is null, return null. If value compared to value, okay, so they are the same. If current is left null and current right is null, but the root is null. So we actually need to set the root to null. Oh, and that's what's happening over here. Root equals remove. So, so if you're removing the root, oh man, if you're removing the root, then it's not going to work, right? Because then then the size is not going to be accurate. Oh my goodness. Why don't we do this? I'll tell you what we're going to do. We're going to cheat. We're going to cheat a bit. Let's do the following. Let's go to size. Let's get rid of the size. Because it's going to make it more complex. And the remove also, it's the mod count's not going to be correct either, because if you don't actually remove anything, it shouldn't change it. But we're going to change it, and the size we're going to also change to simply count. So we're going to say iterator, or iterate over this, and we're going to count. Now this is what they do with concurrent linked lists. I'm not going to be that unhappy about that. I mean, it's not ideal, but it should at least give us the correct answer for the size. This is not how they do it, of course, in the normal tree set. In the tree set, they'll use the proper thing. And the fast fade iteration that here we had, the remove is not implemented iterator. I don't know if I should dare to implement that. Oh my goodness, should I do that? I don't know. I think I'm going to just ignore that one because I don't really want to have that implemented. Okay, I'll just do it like this to test the modification exception. That should work. Oh, so remove shouldn't. I don't want to implement that. So that's going to be this test here. Let's delete that as well. And okay, so I'm also not doing this test. So it's not as detailed test as the list, and it's not completely correct, but at least it passes. Now, what I wanted to show you was not the FIFO queue, but the test unbalanced contains. That's actually what I'm trying here. And if I run this code, let's make it 10 million. So we've got a lot of items in here, and now it takes like a couple of seconds to run, so it's like 3 seconds. But if I do the following, if I go and I put this into a list first, so instead of putting it into a simple tree, I'm going to say a list of string. Okay, that's a list equals new array list. I'm going to add them in there. Import. I'm going to say list.add. Exactly what I did before. This over here. Okay. Then we're going to say collections.shuffle the list. And then once I've done that, then I'm going to iterate through the list, and I'm going to the list, or let's say list.forEach. List.forEach. I'm going to say simple tree add. So I've first shuffled it, and then I'm going to go iterate through it. And even though I first have to make up the list, it's still maybe the shuffling takes too long. This is weird. Why is it taking so long? Okay, it didn't work the way I wanted it to work. So now it's long, now it's slower. Okay, let's do. I think the shuffling is what's taking a long time. Let's put the shuffle up here. Yeah, I don't know. I wonder why that's so slow. It's weird. It's weird. I've got an idea why, but I mean, okay, it's good. It's maybe that's also quite slow to do. Shifting all the arrays of elements around. Well, what I could do is, it's not exactly the same, but let me do this a bit differently, because the demo didn't work well. We're going to say list equals thread local random dot current dot ints between 0 and 1 billion. So it's going to be quite a large range of numbers, and we're going to look for the size will be 10 million. The size of the stream will be 10 million. All right, so it's going to be 10 million between 0 and 1 billion. Then I'm going to take those. So it's just going to be random numbers. I'm not going to shuffle them. They already are shuffled, essentially. Map to object. I is going to be string equals plus I. Of course, it's going to take a while to build up. Oh, I know why it's taking so long. It's taking... No, I don't know why it's taking so long. I thought I knew why it's taking so long. I didn't. Maybe building up the tree was longer. Okay, and then I'll say .toList. So this .toList. We've got the list over here. Hopefully they'll be quicker. Yeah, because I've actually done the shuffling outside of there, and it's still slow. And so now we're going to try and add to the simple tree, and then see whether it contains it, whether it's fast there or not. Let's see how that works. Everything I'm doing is like slower. So, kind of weird. Oh, because I'm looking for something which is not there. That's interesting though, but it should be quicker. It should be quicker because it's not. That's interesting. That's interesting. So I didn't expect that. So if I change this to be sorted, so this is now the random one. If I change that to be int stream dot range 0 to 10 million unshuffled, then it's faster, and it should be quicker. I mean, it should be slower. At least maybe they're doing something else which I'm not aware of. Obviously they are. So contains, you see, the problem with the unbalanced one is that you have basically a long linked list, whereas if it's balanced, it should actually find the element quite quickly. So how does contains work? Well, it does compared to, if it's 0, compared to it returns true. Otherwise it looks, if it's less than 0, it does contains left comma value. Otherwise contains right comma value. So this is kind of weird. I didn't expect that. I really thought, because usually you'd end up with a weird binary tree. We'll have to look at this again. There's something funky going on which I'm not quite sure of, which I didn't expect. I expected it to there's another thing which could be at fault here, and that is the way that the elements are arranged in memory might have something to do with it. So it might be quicker to walk through the memory in order than to go in the different directions. But this is for another day. So I think that's enough for one day. I've got to catch a flight, so I've got to finish this one now. But yeah, if you enjoyed this, I'm going to upload this. The experiment didn't work the way I wanted it to work, but it's a live stream and no practice at all. Just okay, let's go and do this. I think that's obvious. I think that you realize I'm not really practicing anything here. I'm just trying it out and seeing how it works. And well, this is what you get, right? If you don't prepare, you get unexpected surprises. Usually surprises are unexpected. All right. You have a good one. Enjoy the rest of today, and we see you again in a couple of days' time. Bye.